Here we go, still talking about phones. We are getting into, in this video, really the meat of how your phone is able to send and receive information. How do you actually get that Snapchat or that Instagram story from your phone out toward like a cell tower and eventually to like your buddy's phone? And of course, how does your phone receive information, receive a signal from your buddy who just sent you a text or is sending you a phone call or whatever? So that's what we're getting into in this video. All right, I have a warm-up question for you. It says, what do you think, or why do you think we use radio and microwaves to send information? I've said it several times in past videos. Wi-Fi, Bluetooth, 4G, LTE, the type of light that our phones have been using, or that they do use, are microwaves and radio waves. And even when you think of like old school radio, right, AM, FM radio, well, obviously that's also using radio waves. So out of all the different types of light that we know about, from gamma waves to infrared to UV, visible light, why do you think radio waves and microwaves are the predominant form of light use? What do you think? Give me a couple sentences and can you think of why? There's several parts to this, and we'll talk about it as we go through this video. There's several things, including, oh my gosh, maybe you were able to apply what you learned about scattering from the last video. But we're going to answer this as we go. Okay. Here's our big question. I feel like we pretty well have covered this. We got the idea of how we can hear sound, how we can see different colors, okay, combining colors, all that good stuff. We've been kind of in this domain, though we've kind of been looking at kind of alternate things like, you know, we're not sending out gamma waves because we're not causing cancer to anybody. You don't have to be concerned about the waves that are being sent by phones because they're radio waves and microwaves. All right, we haven't yet really gotten too much detail. This is kind of our very last step. So we're looking at this main idea, sending and receiving information. This is what we're in the middle of. Okay, let's just think in general. How can I send information? Let's say I have a piece of information in my head and I want to send it to you. What are some things I could do? Well, I could shout at you, right? And you were in my class. You know, that's the main way I submit or I transmit information. I just yell at you. Now, there's a problem with yelling. One, it's tiring. But also, yelling works over pretty small distances, right? Let's say you were at home because, I don't know, there's some pandemic going on and you're not within shouting distance of me. How else could I send information? Like I could write you a letter, I guess, right? I could bust out the old pen and paper and I could, you know, put in a lot of data, a lot of detail in that letter. What's the downside? Well, it takes time, right? Time to write the letter, and the time for that letter to travel takes a long time. So hopefully there's a better mechanism that would maybe take a fewer or a shorter amount of time. I could send like smoke signals, right? I could tell all of you to be on your roof at 3 p.m. and I'm out there in my home and I'm sending out smoke signals and you're at home and you're going, oh, okay. And to be honest, admittedly, smoke signals are probably faster than if you were waiting for like a piece of mail to go down like one mountain, across the valley, up another mountain. Whereas if there were two people on a mountain and one was sending smoke signals, you can see that pretty quickly. So certainly in some ways, smoke signals would be faster. Obviously, there's a downside. The range is still low. There's another problem with smoke signals. You can't convey a lot of information with smoke signals. I can't write in smoke with a fire. Turn to page 15, show all your work, original equation, plugging in, answer with units. I can show like smoke, no smoke, maybe a lot of smoke, maybe a little smoke. So if I was going to use smoke signals, I would need some kind of code. And to be honest, this is really getting into humans' next steps for how we evolve to send information, evolve technologically, not biologically. Okay, if I was going to use smoke signals, I would need some code. I would need to simplify my vocabulary, my language to match the means I have. And that's still true to this day. After like smoke signals, kind of the first long-range form of communication was using a telegraph. and that was using electricity. You needed electrical wires running either over land or over the ocean. We had telegraph cables running across the Atlantic Ocean. That's how we would communicate with like Europe, of course. All right. Now with this, again, you need, like with the smoke signals, a form to communicate, something like Morse code, dots and dashes. And then once both sides learn that code, you can learn the code and you can send dot, 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 dash, 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 dot, dot, dot. The other person listening in or detecting those signals can be like, oh my gosh, that code means you need help. Okay, all that good stuff. So there's many ways to send information. There's pros and cons. When it comes to wireless information, this is mirroring this. It's the next stage of sending information quickly, which telegraphs did, okay? Sending it over long distances, which the telegraph does also, and also the need to kind of encode it, because you can't describe as much info with Wi-Fi or with telegraphs in the same kind of way as like I can fluctuate my tone and my my volume and my different words and pronunciations. You're a bit more limited, okay? Now, radio waves and microwaves. Okay, why use radio waves and microwaves versus other types? And why do they take over, say, from the telegraph and smoke signals? Well, one, they travel very fast. Okay, they travel at the speed of light, right? Nothing else travels faster. They're also the lowest forms of energy. If you said that on your warm-up, nice thinking. Your battery in your phone doesn't have to drain a lot to send out radio and microwaves. Those are low energy waves. Your phone doesn't have the ability, that battery, to produce prolonged gamma waves, right? Gamma waves take way more energy than your phone can produce. Also, well, it's nice that radio waves and microwaves don't give you cancer. If you said, well, you know, we're not going to use ultraviolet or X-rays because you're going to kill people holding phones, that's not a bad answer. And if you watched our last video, radio waves and microwaves, those are very low frequency, big wavelength waves. Radio waves and microwaves do not scatter, or at least not nearly as much as visible light, infrared, ultraviolet. So that's another reason radio waves and microwaves can travel around the world, through the air, through outer space, to our satellites, back down, and you lose very little of the signal compared to using other types of light. Okay, now let's get into the mechanism. How do you actually send a wave? How do you send this signal? Let's remember what a light wave is, whether it's radio waves or yellow. Light waves are oscillating electric and magnetic fields. So if I want my phone to create a radio wave, I need to create electric and magnetic fields. It's nice because once they're created, remember they self-propagate, but I still have to start it. So let's think, how could I create like a magnetic field? If I can create a magnetic field, then I got a light wave. How do I make magnetic fields? Oh my gosh, how do I create magnetic field? Oh my gosh, it's the same thing we've learned months ago. If I can get an electron moving, wiggling, vibrating, oscillating, moving electrons create magnetic fields, changing magnetic fields create electric fields, and on and on and on. So I have a simulator I want to show you. This is showing like a radio station, kind of old school. Radio stations have antennas. What is an antenna? What does it do? Well, what an antenna is, it's something that holds a whole bunch of electrons, and by passing a current, there's wires in there, you can make those electrons move forwards and backwards. That's what an antenna does. Because when you move an antenna and you move electrons, when you move electrons forward and backwards, you create magnetic fields. That's what you're seeing right now. I can move this electron up and down, and that's going to create oscillating magnetic and electric fields, and vice versa. This is only showing simplified, it's just showing one of the waves. Of course, radio waves are really both. So that's what an antenna does, and that's what your phone is doing. Your phone's job, it uses a computer, it encodes, which we'll get into a little later, it encodes whatever the image or the sound is, and it sends that info to the antenna, and the antenna makes your electrons, the electrons in the antenna, wiggle. And that creates oscillating magnetic fields, that creates radio waves. When it's done sending that signal, it stops wiggling those electrons. Okay, so let's go over this. Your phone's computer makes electric current, right? There's computers and wires and batteries and things. It can make those electrons wiggle in alternating ways, ups and downs, ups and downs. And you can match that like smoke signals. Smoke signal, smoke, no smoke. Morse code, dots or dashes. You can use a code for the electricity. Is it vibrating at a big frequency or a low frequency? That's a code. Or maybe big amplitude versus small amplitude. You could maybe use that as a code. But how you make those electrons wiggle, that's going to change that created magnetic and electric field, the radio wave. And there you have an encoded form of communication. And with this amplitude and frequency, those are kind of the two different ways that you can get those electrons to wiggle. I'm sure you've heard of AM and FM radio, even if you don't listen to it. Well, AM stands for amplitude modulation. AM radio stations, they are encoding information by wiggling those electrons at different amplitudes. That's how they encode it. If you're listening to a frequency modulated station, an FM radio station, well, that's encoding the information by wiggling those electrons at different frequencies. And that presents information, low frequencies to high frequencies, to medium frequencies to low frequencies. There's certainly more detail, like there's pros and cons with doing these two things, one versus the other, which we won't get into. But it's all about getting those electrons to wiggle because that's how we can create, oh my gosh, electric and magnetic fields. So that's how we're able to send radio waves and microwaves. The antenna wiggles electrons, that creates your radio and microwaves. How does the other phone at the other end, or how does a receiving antenna detect a signal? To be honest, it's very similar. I want to show you this animation, and it's very simple. It's just showing a boat on the water. And look at the boat. The boat is moving up and down as water waves are passing. Let me ask you a question. If I increase the amplitude, the height of those ocean waves, would it increase the height that the boat would be moving up and down? Yeah, if I increase the water amplitude, I would increase the boat's amplitude. If I increase the frequency of those ocean waves, would it increase the frequency that the boat goes up and down? Yeah, because the boat is moving because of those passing by water waves. The boat is being influenced by those water waves. The boat is responding to the amplitude and the frequency. Well, the electrons in your phone, not only could I make them wiggle, but a passing by electric field moves electrons. Oh my gosh, do I got to go all the way back? If I have an electric field, which is part of a radio wave passing by your antenna, electric fields move electrons. And then, like the boat, it's going to start moving up and down, matching that signal. Oh, they're going to wiggle back and forth based on that incoming wave, and your phone can decode it. Just like I know the code for Morse code, so if I hear it, I can decode it in my brain. Your phone's computer can decode the signals from the radio and microwave. So let me again pull up the animation. Okay, now I'm going to set this to oscillate, just so I don't have to keep wiggling it. So here I go. Here I am sending my Instagram post. Okay, it goes through the phone's computer, the motherboard, the processor, sends it to the antenna, gets electrons wiggling. Obviously, the wiggling is going to be a bit more complicated, but the basic idea is the same. You got wiggling electrons, that creates magnetic fields, which create electric fields. Bam, you got light. The light travels through space, it doesn't scatter. And here is an electron just sitting in the antenna of another phone. And when a radio wave passes by and its electric field, it's going to apply forces on that electron, and it's going to make it start to wiggle as well. And just like the boat wiggles based on the amplitude and the frequency of the water, the electrons will wiggle based on the amplitude and the frequency of the radio wave. And the computer can decode the information. And your phones use a fancier form of Morse code. We'll get into binary a little bit. We won't really get into hexadecimal or anything, but we'll look at a little bit of that code. This is how phones communicate. This is how all of our wireless technology is communicating. Okay, you get wiggling electrons, that creates radio and microwaves. Okay, those radio and microwaves will make other electrons wiggle in a different location. Your computer can decode it. Bam. That's actually not that difficult in my opinion. Okay, and again, it's based on that same physics that we learned, I think, 2 units ago. Okay, so here's our idea. All right, it's just kind of the opposite of how we send a signal. That's how our phones detect a signal. Okay, last thing, you might think, this is my very last slide, well, all right, Thrasher, I know certainly old antennas exist, like here's a classic looking antenna, even old phones have antennas, but like my smartphone, it doesn't seem to have an antenna. And a lot of cars these days, you don't see a really obvious stick pointing out of it. So what's going on? Do your phones have antennas? Yeah. But technology has advanced and engineers have designed innovative ways to kind of hide those antennas. I know you might be laughing. This is a really old version of an iPhone. But this is one of the first times, or at least I should say, this is a good diagram that shows that for iPhones, where is the antenna? It's not sticking up like this, but it's the wrapping around on the phone. The iPhone 4, it didn't have these nice smooth edges, but it had these very metallic little strips around the edge. That was actually the antenna of the phone. So just like you have an antenna like this, a piece of metal where electrons can wiggle, the outside of the phone has electrons that can wiggle in these metal pieces. To be honest, they may have changed it. I'm sure they've updated it from here, but even pretty recent iPhones, and I'm sure similar Samsung, things like that, if you have an iPhone or you have a phone and you see like this metal strip wrapping around, that's almost certainly the antenna for the phone. And again, to be honest, it gets more complicated. Phones have multiple antennas, one for Wi-Fi, one's for like GPS information, and there's advantages to that we frankly won't get into, but phones still have antennas. You need pretty much a piece of metal that can have electrons wiggle. That's what you need. Okay, so there's the basics of how our phones are able to send and receive information. That's it. Thanks for watching.